Now let me explain the absorption spectra as well as the lambda max of carbonyl compounds. Now acetone is a normal ketone, is a simplest of the ketones. It is a carbonyl compound and is characterized by the presence of a carbonyl group, that is carbon-oxygen double bond. While in case of methyl-vinyl ketone, it is a conjugated ketone where carbon-oxygen double bond is conjugated with carbon-carbon double bond. And as I already mentioned, whenever there is conjugation, there is delocalization of pi electrons. And whenever there is delocalization of pi electrons, the energy level of the conjugate system, it decreases. And hence the compound absorbs at longer wavelengths, resulting in greater lambda max values. And in case of methyl oxide, you find that the terminal hydrogen atoms are replaced with two methyl groups. And how do you identify an alpha and beta carbon in case of conjugated carbonyl systems? The first carbon with respect to the carbonyl carbon is the alpha carbon, and the second carbon with respect to the carbonyl carbon will be the beta carbon. So assignment of alpha and beta carbons is purely based on considering the functional group. Here it is the carbonyl group that we are considering as a reference. So how do you identify the beta carbon in case of conjugated carbonyl system? So the beta carbon refers to the second carbon in a chain related to the functional group. So here the functional group is the carbonyl group. It can also be an alkene group. So with the increase in number of double bonds, you can see the lambda max value increases. Acetone, it is 187 nanometers. In case of methyl vinyl ketone, it is 230 nanometers. And with alkylation, in case of methyl oxide, you find additional presence of two methyl groups on beta carbon. So with the increase in or addition of alkyl groups, there is further increase in the lambda max. So bathochromic shift or red shift is due to two reasons. One is due to conjugation, that is increase in the number of double bonds and that are in conjugation with each other. And second reason is alkylation, that is presence of alkyl groups. So in case of methyl oxide, both the factors are contributing towards the bathochromic shift or the red shift. So there is presence of conjugation as well as presence of alkyl groups. And how to theoretically calculate the lambda max for a conjugate system, that is conjugate carbonyl system. Now let's try and calculate the lambda max for the methyl oxide, which is a conjugate ketone. Now the base value for alpha beta unsaturated ketone is 250 nanometers. So this is as per Woodward-Fieser rules. So as per Woodward-Fieser rule, any conjugate system where you find the presence of alpha beta unsaturated ketone, like in case of methyl oxide, you assign a base value of 250 nanometers. So what is base value? Now base value is nothing but a numerical value assigned to a conjugate system, which is a alpha beta unsaturated ketone. And when you observe the structure of methyl oxide, you find that in addition to the presence of the alpha beta unsaturated ketone system, there are presence of two alkyl groups, that is two methyl groups covalently bonded to the beta carbons. So an additional increment value of 12 is given for each methyl group added to the or covalently bonded to the beta carbon. So in case of methyl oxide, you find two methyl groups covalently bonded to the beta carbon, and therefore the theoretical lambda max value will be 215 plus 12 plus 12, that is 239 nanometers. 215 because the base value of 215 given for the presence of this alpha beta unsaturated ketone system in methyl oxide. And why 12 is added twice because two methyl groups are covalently bonded to or attached to the beta carbon. So for every alkyl group attached to the beta carbon, you add a or you give a increment value of 12 nanometers. So here you find two methyl groups attached to the beta carbon, and therefore you add 12 nanometers twice. And that is equal to 239 nanometers. So 239 nanometer will be the lambda max theoretical calculation, but the practical observed value is around 250 nanometers. Now sometimes both the theoretical as well as the practical experimental values may be the same, and sometimes it may vary. The values will be very close. So methyl oxide is a conjugated ketone where the carbon-oxygen double bond is conjugated with carbon-carbon double bond. And there is delocalization of pi electrons due to mesomeric effect. Now mesomeric effect refers to polarity produced in a molecule as a result of interaction between two pi bonds. And the mesomeric effect is represented by a curved arrow where the arrow end represents the mobilization or movement of loosely held pi electrons towards the more electronegative oxygen atom. So there are two driving forces for the delocalization of pi electrons in case of alpha beta unsaturated ketone. First is the greater electronegativity of the carbon atom, which is around 3.5 on the Pauling electronegativity scale. And second is the easy mobilization of the pi electrons as it is loosely held. Now the conjugation, it decreases the energy difference between the HOMO and the LUMO. That is the energy gap between the bonding pi molecular orbital and the anti-bonding pi molecular orbital. Now the pi electrons in the ground state is represented by symbol pi, while the pi electrons in the excited state is represented by symbol pi star. So pi to pi star transitions are observed in compounds with unsaturated centers like alkenes, carbonyl compounds and aromatics. So I have tried to cover all these three in this video. So delta Ex is the energy required to bring about transition of loosely held pi electrons from the ground state to the excited state in case of acetone. And delta Ey is the energy required to bring about transition of pi electrons from the ground state to the excited state in case of methyl vinyl ketone. And delta Ez is the energy required to bring about transition of pi electrons, loosely held pi electrons from the ground state to the excited state in case of methyl oxide. And with the extended conjugation, the energy gap will be further reduced. So the lambda max value for a compound depends on the energy difference between the two levels, the ground state and the energy state levels. So the energy difference for acetone is delta Ex, energy difference for methyl vinyl ketone is delta Ey, and energy difference for methyl oxide is delta Ez. And with extended conjugation, the energy gap will further get reduced. So with increase in conjugation, there is increase in delocalization of pi electrons, and with increase in delocalization of pi electrons, it lowers the energy gap between the HOMO and the LUMO, that is ground state and the excited state. And as an outcome of this event, the absorption of the U visible radiation by the molecule occurs at a longer wavelength. And that is how the lambda max of the compounds increase with increased conjugation, because their absorption occurs in the visible region. Thank you so much for watching my video. I hope you enjoyed it, and I'll meet you in my next interesting tutoring session.